Looks like we can officially start. Welcome back, everyone. I don't have a whole lot of announcements to talk about, but let's get them out of the way anyways. I should have exam one grade by Friday evening. It's not a guarantee, but I think I'm on track for making that happen. If I don't get it done by Friday evening, it could spill over into the actual weekend, and that's just not great. So I'm going to make a really good effort to try to get them all graded up. Also in section 7.8, we're nearly done with it, but we have one more example we're going to go carefully through and see how it goes. And then we're going to go into chapter 8, further applications of integration, starting out with finding a length of a curve. Or they call it arc length, but really they're just meaning what is the length of any curve from A to B, like in this graph here. Turns out it's simple to state the formula. It's kind of hard to derive. I'll leave it up to the class if we want to look into the derivation for that thing. But any questions, folks, then with the announcements or anything at all? Okay, well, let's jump back in. 7.8 is just about done. So let's go to, oh, here's there. That last problem. So this one was edited. There was a domain error, I think I mentioned on the last one. So we just changed out the denominator for a more reasonable problem. But we indicated last class that this is definitely improper integral type 2 because the integrand 1 over x minus 1 cubed is not continuous at 1. That's the discontinuity. Let's put just here a quick note. Discontinuity. That means this is one of those slightly longer problems where we have to do extra analysis on this. We need to break this down into two different integrals across the inequality. Now, our first step would be then to write out, excuse me, that this is now a definite integral from 0 to 2, 1 minus x minus 1 cubed dx equals, we go from 0 to 1, so we're into this boundary here. Instead of x minus 1 cubed, just to think about integrating, I'll write it as x minus 1 power negative 3. It's actually kind of simpler to write it that way anyways. Then we integrate from 1 to 2. Same exact integrand, x minus 1 power negative 3 dx. After that, we have to write these in terms of limits. So let's take a look at this one. That's going to turn into the limit st goes to, st goes to 1. We're heading off towards the discontinuity. That means t is in this location, so we have to be heading towards 1 from the left. Then we integrate from 0 to t. And so far, this is pretty much what we've done. We've taken the discontinuity, threw in a variable where the limit is heading towards that discontinuity, strictly coming in from the left, of x minus 1 power negative 3, and then we just do it all over again. Plus another limit, st goes to, well, it's always going to the discontinuity, 1, but we're integrating from 1 to 2 now, so that means we're going to 1 from the right. So we'll include a superscript with a plus sign on it. So from t to 2. So one discontinuity in the middle just causes a kind of a mess of these integrals. X minus 1 power negative 3 dx. And if you like to label them, you could call this I1, I2. Up to you. Sometimes that's a good way to kind of organize the information, especially if they both converge. We're going to have to eventually say the original integral is I1 plus I2, putting our answers together. But now we need to test them out and see what this will equal if it converges or show that it diverges. This is the preliminary analysis, and that's what's being mentioned in the assignment right here. Correct limit notation is required for full credit. So we have to put in the limits here, breaking up the integrals is what's being mentioned by those instructions. So let's give them a try. They both look just about the same to me. I don't know if one would be more divergent than the other. So let's just try out I1 and go from there. So I1, limit st goes to 1 from the left. We already have I1 indicated here, so let's just go ahead and take the antiderivative. It'll be x minus 1 to power negative 2, so we'll divide by that negative 2, and evaluate from 0 to t. So I1 turns into this after the antiderivative. Let's write that this is equal to negative 1/2. I'm just trying to get that constant out of there so we can focus on the function that varies. Limit as t goes to 1 from the left of 1 over x minus 1 power 2, evaluate from 0 to t. Didn't do much. I just changed the exponent to make it positive, factored out negative 1/2 to the far outside of the limit. So now this is just a routine evaluation. It'll turn into negative 1/2. Something happened to my 2. There we go. Limit as t goes to 1 from the left. First, we'll plug in a t, so it's going to be 1 over t minus 1 squared. Minus, throwing in 0, well, this is just 1 altogether. You would have 0 minus 1 squared, so it's just a 1 over 1. So we need to take that limit there. This is essentially the review part from Calculus 1, looking at these kinds of limits. Anyone would see what happens to this in the limit?
Goes to infinity?
Yeah, absolutely. A good call. This wouldn't be positive infinity. Due to the power 2 right here, t heading to 1 from the left actually wasn't a big part of this problem. It does matter in some of the other problems. That's why we're so careful with the single-side limits, like if a natural log is involved. But this one, you're just getting closer and closer to 0. You're squaring it to get positive values. That whole part goes to infinity. Then due to the negative constant out front, we'd say overall, this goes to negative infinity, which means it diverges. And that's actually fantastic. If it diverges just one integral when we split it up into 2, now we can give a whole conclusion and say the original integral diverges itself. So let's say, therefore, the definite integral from, I forgot what it was already, 0 to 2, it's actually right here, of 1 over x minus 1 power 3 dx is divergent. So that's just lucky, but I bet you both of them were divergent, in fact, in this particular problem. We did one problem with improper integral type 1 where we weren't lucky. We picked I1, it converged, but the second interval, I2, diverged. So it was almost a wasted effort in that sense. So whenever you're having to split this off in 2, always try to find one that looks to be divergent. Try that one first. That could cut the work in half potentially. But that's the conclusion on this one. It's telling us that with this discontinuity, there's no concept of the area under this curve. The area just grows and grows as this limit gets closer and closer to 1 from the left. Well, any last questions, folks, with working through improper integrals? Okay, these things are definitely an adventure. The homework set isn't too long, but one thing to watch out for in the homework set is that some of the problems are worth 10 points. Generically, all my problems are 5 points each, unless I just feel like these problems stand out. They're extra effort among all the rest. So just to make it worth your while, all the extra writing, those are like double problems. Well, we did it, folks. That's the conclusion of chapter 7. Congratulations. It's a pretty tough chapter to get through. Now we're converting back into dealing with applications of the integral. So the actual antiderivatives we have to take, the improper integrals we deal with, aren't too bad, except in chapter 8, I think 8.1 has some of the harder integrations to get through. 8.2 is a little bit easier, and we'll see the reasons why. So we're looking for arc length, which means, well, here's the formula. We're trying to find the length of this curve right here. To do that, we have to use a lot of different tools in calculus. And so here's how the notes start. First, let me make sure I saved this. By the way, if I ever forget to save something and just the notes are missing, let me know and I'll come back and correct that. There it goes. So lots of information to start out. It says on our first definition for arc length, consider the curve C defined by y equals f of x, where we know f is at least a continuous function from the interval a to b. So let's just draw that out to start with this definition, see what we're dealing with. I'm going to print down a curve, kind of generic, like what we saw on the Moodle page. focusing on quadrant one just to make the drawing clear, not because it has to be there. We're going from A to B. The curve is y equals f of x. Let's say it starts here, ends up way out there. And if it was a straight line, no problem, right? We'll just use Pythagorean's theorem, find the distance between points, and everything's done. We go home early, go to weekend early. The trouble then is if it does something like this instead. Now we got a problem. Finding the length of that curve is not straightforward, but we can make it happen. The way to think about further applications of integration is a real application of integration is using this. Some way, somehow, we need to put in a limit of a Riemann sum when we go to calculate that length. If we can find a Riemann sum, something along these lines, we convert to a definite integral. So that's what the applications are really all about in calculus. Get a Riemann sum, and then just use the definite integral fundamental theorem of calculus. That way we're not always working so hard. But to start out, we have to crawl through the definitions. We do have to work hard for a little bit. So if we want the length of this curve from A to B, we divide A to B into n subintervals of equal width delta x, which is b minus a divided by n, to give all these endpoints. So we already have one endpoint A. Let's call that x naught. Let's let that one be x1. This is x2 and ran out of space. So this will be x3. So n equals 3 in this diagram. So not too much drawing at least. Then we approximate the length of the curve by putting down points and just finding the distance between all of these points here. So let's put in, well, there's our first point, P naught. X1 gives us a second point, P1. X2 gives P3 here. And this would be P4. So now that we have 4 points, we can do the kind of natural thing we were talking about earlier. We can find the distance of straight lines, no problem. So we can find that distance, and that distance. Those distances would be given this way. The distance from, say, P naught to P1, just for one example, would be the square root of, we would take x naught minus x1 squared plus y naught minus y1 squared, and just start calculating each one of those distances. It's a rough approximation, but as n gets larger and larger, say, as n goes to infinity, like up here, we start to get a better and better approximation, and we'll call that the total length. The trouble is, if I just put a limit in front of these things, it is not so easy to actually calculate that limit. Here's what it looks like. As it stands, the length of the curve or we could just call it arc length for short, is now this. The length equals the limit as n goes to infinity of the summation as I goes from 1 to n of the distances from pi minus 1 to pi, which are essentially these kinds of things. Somehow, some way, we have to turn this into something that is a little bit more reasonable to work with, so we can use the fundamental theorem, turning this into an integral. The author provides a pretty decent derivation on this. I shouldn't say pretty decent derivation, it's an excellent derivation. This is like the 8th edition or 9th edition of the book. And so he says that in the end of the day, this is what it turns into. Kind of impressive in a way, because we're looking at a complicated distance formula, but it just collapses to that. This is in Newton's prime notation. If you're a fan of Leibniz notation, that's the same formula, just different stylistic choice there. So I'll leave it up to the class. This is the choose your own adventure part of the day. Would we like to see the derivation, or should we trust the formula? Your choice today. Let's give it a try. Awesome, let's give this a derivation a go. I have some cheat sheets here just in case I lose my way. It's kind of a nasty derivation, but it's a good one. It's worthwhile. We won't do too many in chapter 8. This one is optional, but I think it's a good choice because we just hit on a lot of topics that are important in calculus. So here's how it goes. Oh, sorry, you missed the chats. Zarek says, sorry if I'm overthinking this, but is there a reason why you skipped P2 on the graph? Oh, there's no good reason for that. Thanks for spotting that, Zarek. I think I'm just tired and forgot how to count. So let me put that as P2 and then P3. I should have noticed the problem because this is a picture with n equals 3. So second point, third point. Thanks for spotting that. Oh, Ed, that's just a further on discussion. Thanks for spotting that, folks. So let's give this a try next. What we need to focus on is that. That's where all the interesting things happen. The notation is a little bit weird for the summation. Think as I is 1, this is P naught to P1. So we're just finding that distance. But we need to do it out generically, so let's write this out. Kind of like what's above here. But now let's put in distance from Pi minus 1 to Pi is going to be equal to square root of, well, we do have one trick right away. X naught to X1, that's just the distance from here to here. That's simply a delta X. So you can throw a delta X right in this location. It's going to come out as delta X squared. Does that step there make sense to folks? Awesome. Delta X is important because if we're looking at the definition of the definite integral, you have to have that delta X somewhere in your Riemann sum. That's why this is a problem. There's no apparent delta X anywhere. Our second problem is delta X cannot be in the square root function. It has to come out of here somehow. So here's delta X, quantity squared. We can't just simply factor it out and leave some behind. So we need to deal with this right here next. What do we do with y naught minus y1? Well, one thing we can say right away is those are function values, right? So you could say that's plus f of x naught minus f of x1 squared. So we're getting closer and closer to where we need to go, but a delta x has to come out of that spot, and it needs to be to the power of 2 so that we can factor it out of the square root, and then place it right there in our limit of Riemann sums. If we can't get to that step, we're kind of dead in the water with this stuff. So this requires some new idea. And I would have never have thought of this in 100 years, but someone did. It's the mean value theorem out of nowhere that's needed in this. So here's the mean value theorem for a review on this. The mean value theorem needs some information. We have to have continuity on the closed interval from A to B. Let's double check that. Yes, we're continuous from A to B, so all set there. However, we also want differentiability of the open interval. Nothing in this problem said we had differentiability. So there's more going on with this problem. We scroll down below. What we want is a smooth curve. We're going to allow for f prime to be continuous on AB, which would mean f prime is differentiable on AB. So that's a required condition in order to use the formulas that we're going for. The derivative has to be continuous on the closed interval from A to B. That's a pretty strong condition, and that's what makes it a smooth curve altogether. So let's give another extra assumption. Let's put this in purple or something because it is a new assumption. We must assume that f prime of x is continuous on AB. That would mean the derivative f prime exists on the open set from A to B, which would then mean condition 2 is checked. We have continuity, we have differentiability after throwing in the extra condition, admittedly, we had to sneak that in. Then it says there'll be a number C between A and B such that this happens. The derivative of f at C turns into this approximation, right, or excuse me, this average rate of change. Or if you solve for the distance f of B minus f of A, you get that expression there. It's a little tricky how this comes together. The trickiness is that A and the B is going to be from an xi minus 1 to an xi. So we're using x values for A to B. So let's write this all out. We'll say here, by the mean value theorem, there exists, let's call it xi star. I'll just highlight a generic interval. Imagine we're going from x1 to x2, but we have to describe it as xi for full generality. There exists an xi star in the open set. Let's double check that. The condition is our xi's, the c that we're describing here, it's in the open set. It doesn't actually take a boundary point, A or B. So there's an xi star in xi minus 1 to xi such that the derivative, or let me say this a different way, f of xi minus 1. Oh, hang on. Let me double check what I have here. I'm looking at my subscripts and I think I got a little mixed up with this. I'm going from pi to pi minus 1 to pi, which means subscripts are always kind of nasty with this thing. Oh dear, there we go. This should have been xi minus 1 to an xi. Sorry about that. I think I just copied that over, but I was trying to go from pi minus 1 to pi, not p naught to p1. So just a quick subscript change there. That's a little messy. Let me try a little bit better with that penmanship. F of xi minus 1 minus f of xi. So we're trying to talk about that. That's where I noticed the subscript problem. F of xi minus 1 minus f of xi equals, in the mean value theorem, that's those 2 points right there. It'll be the derivative f prime at xi star times xi minus 1 minus xi. So here's f prime, xi star, xi minus 1 minus xi. So we got that. This thing in blue, by the mean value theorem, turns into that. But here's a new trick. That's just the distance between the intervals. So that is, once again, another delta x. We're starting to get what we were going after. So this thing in blue turns into that now. So now we can finally proceed through this distance right here. Tying it all together, this becomes the square root of delta x squared plus, so a bracket going this way, f of xi star times another delta x to the power of 2. Power of 2 right here came from the old power of 2 out here. So now we have delta x squared. Delta x squared, that means you can factor this out of the square root. It turns into delta x square root of 1 plus, oh, and I forgot a symbol there. That was meant to be the derivative coming from this location. There must be a prime there. So f of prime xi star squared. So that's what's going to do the job for us. The length is this limit, but now we can say, therefore, the length equals the limit as the number of those intervals goes to infinity of the Riemann sum, summation as I goes from 1 to n, of, we're putting in this square root first, root 1 plus f prime xi star squared delta x. So that's finally our Riemann sum. The big takeaways in this derivation is mean value theorem does come up a good amount in calculus 1, a little bit in calculus 2, but it makes a resurgence in calculus 3. For folks taking up to calculus 3, this is just a good thing, good time to review the mean value theorem, how it works. But the bigger takeaway is the definition of the definite integral says you actually don't have to do this limit. The moment we turned it into a Riemann sum, because we have the delta x, the derivative of f, but at a sample point in the intervals, it's now just a definite integral. Here's how it goes. The sample point xi star just turns into x. Delta x turns into dx, our common notation in the integral. So this now is equal to the definite integral from a to b of the square root of 1 plus f prime of x squared dx. So that's how it all comes together. But again, the way to really do this is your curve that you're trying to find the length of has to satisfy certain conditions. It's got to be a smooth curve, meaning the derivative is continuous. I'm not going to ask any questions that don't meet that criteria, but I'm just harping on that because you can take these tools, apply them to the curves that don't meet that criteria, and get weird answers. What went wrong was the criteria never was met. That's why the formula could fail on different kinds of curves. Any questions at all, folks, with the full derivation?
Right, so by smooth curve, you mean it is not like a sharp, for example, curve like an angle?
Yeah, that would break the differentiability, absolutely. And also, the derivative itself had to be continuous, so there can't be any issues on the derivative as well. Well, let's take a look down below. That's the condition that we had to use. And finally, that's the theorem. If the derivative is continuous on the closed domain from A to B, then we have a nice smooth curve, and the arc length of the curve C, defined by y equals f of x, is either right out this way, or if you prefer Leibniz, that way. Kind of a remarkable formula, and what's kind of neat about it is it does look like Pythagorean's theorem was used, but some extra factoring happened. That's why there's just a 1 plus the derivative. The only reason the derivative is there is because we use the mean value theorem to derive this formula. Kind of a slick way to make that happen. But now we're going to apply this and find lengths of curves. Any questions so far, folks, before we jump into that first example? Okay, now I had a bit of a comment I mentioned before. Section 8.1, in my opinion, is a little bit harder than section 8.2. That's because when you go to integrate that thing, the algebra you take is finicky. You have to take certain specific steps with the goal of trying to cancel the square root. That's our major target. So there's no harm in starting off by saying, well, on the domain from 1 to 3, the derivative of this would be continuous. There's no problem with that. But we want to find the length of, or the length of that curve, which is the definite integral from 1 to 3 of the square root of 1 plus dy dx, or you could put f prime here if you prefer, squared dx. Really, almost all of the work in these problems is simplifying the integrand right here. So I encourage you to start there. Let's divide this up. I wouldn't actually carry this whole formula with the integral over because you're writing down the integral sign of the dx without actually doing anything but algebra in the middle. So let's focus on first, if you like a sequence of steps, definitely you have to calculate the derivative. So let's calculate f prime of x or dy dx, your choice in notation. By the way, if you are going to calculus 3, then it's a good idea to get comfortable with the Leibniz notation. It's used tremendously in that context. Well, our function is y equals x cubed over 3 plus x power negative 1 times the fourth. So you could visualize it that way for the derivative. We would get x squared minus 1/4 x power negative 2. So we've got a derivative in that helps out. So this is x squared minus 1/4 x squared. So step 1, we're working inside, think order of operations. Next, we're going to square that. So dy dx squared, or if you want to go a little bit bigger, you could put in the +1 here at this stage as well. Less steps, but same work. Dy dx squared. So now we're looking at the radicand, the thing under the root. This is 1 plus x squared minus 1/4x squared squared. And we wouldn't just want to simply put a root on that to try to integrate it. I don't know how I would integrate something like this. It's just a giant mess in its current format. So what we actually want to do is try to expand it and factor it again. Think of it in these terms. Because of the root, this would be an easy root if that was just gone and you have a power 2. You can simplify and be well on your way. But it's the +1 which is making everything complicated. So here's our next step. This is 1 plus. If you FOIL this all out, you'll get x power 4 Multiplying here would give you negative 1/4. Multiplying here again, when you're FOILing, would give you negative 1/4 again. Altogether, that's negative 1/2 in the middle term. And then finally, square this, you get plus 16, square the whole thing, x power 4. So let's simplify this down further. This turns into x power 4 plus 1/2 plus 1/16 x power 4. Again, kind of weird algebra in a way, right? But once you get here, this is actually excellent. That is a perfect square, well, not a polynomial, but it's a perfect square expression. You can now write this as something to the power of 2. You would take x squared from the first term. The sign has to be positive because of the signs here. From the last term, you would have 1/4x squared. Almost what we started off with right here, but we're landing on that thing there. You could double check. Boiling this out would give you x squared times x squared, x power 4. You then multiply this way twice, but that's a fourth plus a fourth for the half. Then when you square this, that's the 1/16 x power 4. After we do all that, step 3 is just put it all together. Any questions first to this stage? Okay, so down below, let's scroll down here. We have that the length is finally equal to, let's put a little therefore, just to say, by all of this algebra, we can now therefore say the length is the definite integral from 1 to 3 of this square root, but 1 plus dy dx squared we found to be x squared plus 1/4x squared dx. So that's what this turns into. Oh, and I forgot my power 2. There it is. So now it simplifies in a major way. It's just the definite integral from 1 to 3 of x squared plus 1/4 x power negative 2 dx. So we're on the relaxing portion of the problem. This is the calculus 1 integration. Any questions to this stage? Okay, we'll do a sanity check on this one just to see if we even believe that's the right length. But let's first finish off this problem here. Antiderivative on that term will give us a third x cubed. This one is going to give us negative 1/4x. This turns into a power negative 1, multiplying that fourth, and so I just put the x down in the denominator. Evaluate all of this from 1 to 3, and we will get, that's kind of a tedious one. First 3 goes in, a third times 3 cubed. So that's just a glorified 9, minus 1/4 times 3, minus, the 1's not so bad, we'll just get a third minus a fourth. Now it's all just kind of arithmetic from here, but let's sort it out. This is turning into 9 minus a 12th. And what is this? This will be 4 minus 3. So it looks like a 12th, right? So minus a 12th again. Is that right? So 4/12 minus 3/12, 1/12. So minus a 12th again. Thanks for the double check on that. Arithmetic is tedious when you're pretty tired. So it's 9 minus 2/12, which is 9 minus a 6th. So that means it is 54/6 minus a 6th, or 53/6. Or if you just put in the repeating decimal in your calculator, I'm totally fine with that too. But our thought here is that that length should be 53/6. Who knows if that's true, but you can definitely see if it's reasonable. Any questions first with the full process? Oh, let me double check. I think I made a mistake right here. That was 3 cubed. I wrote in 3 squared on accident. Good check on that. So yeah, that should have been something else, but with the correction there, it should have been a 9. My mistake on that one. I need to carry my exponents a little bit better. I'm dropping subscripts and exponents today. You can tell it's the end of the week, I guess. But let's take another look at this then. What we want is just the good old Desmos calculator. plug in the function with that domain, y equals x cubed thirds plus 1 over 4x on domain. So you need a curly brace, 1 less than or equals x, less than or equals 3. And we're trying to find the length of that curve. But you know what you can always do is you can just take, say, a point here, and just find that distance with Pythagorean's theorem. That would give you pretty good information. Let's see if we can do that. Right down here, this is at 1 and 0.58. Roughly. Up here at the top of the curve, let's see what that one is. That's 3, 9.08. So now just use the ordinary distance between points. Square root of, well, I guess we could just calculate it directly. Let's put it inside here and calculate it. So go square root. Take the difference of the x coordinates, so that's just going to be a 2 squared, plus the difference in the y coordinates. I'll just write that out as 9.08 minus 0.58 squared. And the length with a pretty blunt approximation, just a straight line, is 0.873. Ours should be longer, right? It's a longer distance if you curve to go from point to point. So let's take a look. 53, 6, 8.8. That actually tells us we're probably almost definitely correct. That's overwhelming numerical evidence. We have the right length of that curve at that point. We still could have made a mistake, but at least we're pretty close. Well, any questions at all, folks, with looking at a check on it? Okay, in case you decide to try that out on the homework, just to see if your numbers are in the right ballpark, let's just put this down below here. So that's this whole section 8.1. Honestly, it's not as intense as, the very first day of class, integration by parts, then trigonometric integrals, then trigonometric substitution. Those are pretty tough sections. The tough thing about this is just knowing the right algebra to make this integrand work out. Well, we'll try out a couple more and see how they go. Any questions or comments at the moment? Okay, so here's a kind of a wacky one. It goes x equals a third of square root y times y minus 3. This is weird because we have a domain on y. Everything's backwards. The role of the variable x and the variable y have been totally interchanged. But that's completely fine. Whether you view x as the dependent variable or the independent variable is completely immaterial. Formulas work out the same way. We just have to reformulate it for the right roles of x and y. So if you have this problem coming up, just write out that the length is going to be integrate from the domain given on y, that's going from 1 to 9. If y is being given as limits of integration, there's not a dx anymore, there's a dy going right here. The integrand is going to be a 1 plus, not a dy dx. This is where Leibniz actually helps out quite a bit in this section. You want to put in dx dy squared. So all I've done is taken the original formula for the length. Instead of dy dx, interchange x and y here. Instead of dx, do dy. And then you're in good business. This will work out just like before. But just like before, we have to be really careful with the algebra. So we'll go through it methodically, trying to simplify the integrand. Any questions at all, folks, with the format of that formula there? Okay. Well, if we're going to differentiate it as it stands in that location, that's a product rule. But if we distribute first, we sideline the product rule and have a nicer derivative. So I'd probably start by just distributing 1/3 root y into the group. X is 1/3 root y times y. Then it's going to be minus root y. Then a little bit of exponent surgery is going to give us that root y is y power 1/2 times y to the power 2/2. So we have y power 3/2 on that first term. 1/3 y to the power 3/2 minus y to the power, well, you know what? That one's a good one by formula, root y. Next step, we need the derivative of x. And again, this is why Leibniz notation is kind of nice. Putting down x prime just kind of looks weird on paper. It's not saying exactly what you mean. A lot of people would think, well, derivative of x is 1, but that's not what we mean at all. X is the dependent variable. We want to say dx, dy. The derivative of the function x with respect to its independent variable y. So Leibniz notation is nice because it's highly descriptive. It becomes a matter of survival in calculus 3. So ordinary derivative here, we'll have 1/2 times 3/2. The new power of y is 1/2. So if you like, you could put it root y instead. There's a shortcut on this one. Let me know if this seems weird or foggy. Whenever you take a derivative of a square root, this always happens. The root goes down below with a factor of 2. Oh, I think I just made a mistake on copying that. Thanks for spotting that. That should have been a 1/3. I think I just need to go a little bit slower with my pen. Thanks for the participation, folks. For the correction there, the 3 should have been copied down directly that way. Thanks for spotting that again. Other questions so far? Okay, well, it simplifies just a touch. We have 1/2 root y minus 1/2 root y. This might kind of look sort of familiar in a certain sense. The trouble we have with some of these integrals is that it's actually really hard to invent a problem, because if you just throw down a random function, the chances are that antiderivative could be next to impossible, or in fact impossible. You might have to just approximate it. So sometimes the algebra does look familiar because there's not a lot of different examples. Next thing we're going to do is go 1 plus dx dy squared, which is 1 plus 1/2 root y minus 1/2 root y squared. So foiling that out, we'll get 1 plus that first term squared. So this will be 1/4 y. Then when you multiply here to here, you're just going to get negative 1/4. Sounds familiar? If multiply here to here, it's negative 1/4 again. So all that conveys or goes down to a negative 1/2 in total. Finally, once I get the eraser working, finally, once you square this portion, we just get 1/4y. So that's the result of foiling all that out. Any questions, folks, to that stage? Okay, again, almost deja vu on this one. The positive 1 minus 1/2 will give us a positive 1/2 by the red dot. So on the next step, this is 1/4 y plus 1/2 plus 1/4y. And it turns out that also factors. It just looks really weird this time. But if you're thinking about the last problem, same pattern occurs on this. Anyone see what should be right here in the first term? Sorry, say again.
1/2 y. Y/2.
It's going to be 1/2, but it'll be just a root y, the first one right there. So good call. It's just going to be pretty much that. Then plus in the middle, and same on this one, 1/4y. When we go to factor this whole thing, will turn into 1/2 root y. I'll leave it up to the class on this though. Do you believe it, or should we check that out just to be sure? Good call. Let's check out this thing. So if you're going to FOIL that out, you're looking at, just to put things in a more methodical approach, you have 1/2 root y plus 1/2 root y multiplied by itself again. Multiplying this way is going to give us 1/4 y. Here to here, the root y in the numerator, root y in the denominator cancel out, so it's just plus 1/4. Then next, Multiplying here to here, same cancellation with the square roots, we get plus a fourth. And here multiplied by here, well, root y times root y is just y, so this is plus 1 over 4y. The middle terms right here turn into 1/2, which is what we were gunning for the middle term. So that tells us that really is the right factorization. Essentially, all I did was take the square root of the first term, square root of the last term, put them in, and raise it to power 2. But again, pretty weird factoring. It looks more believable when you factor this way, because we're used to reducing the power when it's not like a fraction, power 1/2 for the square root. This, I think, always looks better on paper, makes more sense. But if you must factor, then you can factor this as well. Just looks weird. Any other questions, folks, with those first preliminary steps? Okay, so the whole purpose to all of these weird bits of algebra was to take that and put it all right here. So here's our next step. We're just going to finalize the answer. The length is a definite integral from 1 to 9 of the square root of, let's just throw it in to connect the dots, 1/2 root y plus 1 over 2 root y, all to power 2, dy. So massive simplification, because we took the time with the algebra, we just get 1/2, or at y to power 1/2, just to make the antiderivative look better. And same on this one, plus 1/2. This will be y to the power of negative 1/2. So that's our integral that we're looking at next. Now, to find antiderivatives, we'll go and take that this is 1/2 times a little bit of space, add 2 over 2 to get 3/2 on that, multiply by the reciprocal, 2/3. And then that was so fun, we just do it again over here. So plus 1/2, give it a little bit of space, put in the new exponent. We're adding 2 over 2, so it's 1/2. The reciprocal is 2 over 1. So all that evaluated from 1 to 9. And let's simplify it before the evaluation. No reason to carry all this stuff in when we're evaluating for the upper limit, lower limit. Might as well simplify it now, less writing overall, I think. So we'll have 1/3 y to the power of 3/2 plus, might as well just call that one square root y, evaluated from 1 to 9. So we'll plug 9 right here. We get 1/3. 9 to power 3/2. That one's not so bad. We can sort that one out. Plus root 9, not bad either. Then from the lower limit, we're plugging in a 1. 1 to any power is just 1, so this turns into 1/3 plus 1. So we need to work this stuff out. This is not too bad. Let's see. Just for more of an exponent review, if you see 9 to the power 3/2, you can think of this as square root 9 to the power 3. Square root came from the denominator 2, so square root 9 is 3 to power 3, so we're just getting a 27. So this is 1/3 times 27, giving us a 9. So again, feels like deja vu a lot on this problem. Square root of 9 is 3 minus 1/3 minus 1. So this is turning into 9 plus 2 minus 1/3. So 11 minus 1/3. We're getting there. The 11 is 33/3 minus 1/3 for 32/3. But again, that's just a bunch of arithmetic. If you put this in a calculator, gave me the repeating decimal, that's exact. I'm happy with that as well. But we've got a length, folks. The length of this curve, kind of a weird one, from 1 to 9 is 32/3. Not too sure when this will really affect us in ordinary day-to-day life, but it's nice to know that you can find the lengths of these curves. Who knows? This could be the trajectory of a projectile, or it could be a cable hanging from one pole to the next. These are very practical problems for finding the lengths in a real applied setting. Any questions at all, folks, on maneuvering through this kind of a monstrosity of a problem? Okay, the thing to notice is there's always this algebra phase where you're trying to find a way to finagle a power 2 to cancel the root. Then it's all kind of just pretty much nice integration from then on out. So if you can get through this, you're in good shape. If you get tied up on the algebra at any time, don't hesitate to email me. I'll be happy to point out some hints or directions you could go to take it. Well, we're not going to finish these notes today. There's lots going on in this document, actually. But I think we have time for one more. So let's make the next problem our last one for the day. We'll see if that makes sense. So this is a weird one. We're taking the natural logarithm of cosine x from 0 to pi over 3. I'm just curious at this point. Let's see what that looks like. I don't think I've actually plotted this one. So y equals natural log cosine x. It's got a cool shape, it looks like. 0 less than or equal to x, less than or equal to pi over 3. Well, it did look cool, but we're just looking at that portion right there. Without the domain, the whole thing looks like a bunch of repeating things with vertical asymptotes. Pretty wild. Oh, I don't think I can control Z to break. Oh, there it is. So we just need the length of that curve. Notice it should be pretty close to square root of 2. That's the distance of the diagonal on this unit square right here. So we need an answer that's in that neighborhood. So to get this one, there's no tricks with the variable. Y is the standard dependent variable. So I usually just write this out as a start. It helps us remind us of what the formula is, what the next steps should be. Integrate from 0 to pi over 3 of the square root of 1 plus. And for the folks who are fans of Newton's prime notation, let's use it this time. F prime of x squared dx. Only downside is this is given as a y equals, but keep in mind in function notation, you can always call that y equals f of x. So f of x is officially natural log cosine x. Prime notation is nice because it's compact, feels like a lot less writing. You're a little bit faster with it. First step we have to take is differentiate that. F prime of x, well, we're differentiating with a chain rule. First thing it does is put cosine in the denominator. By the chain rule, we have to now multiply by the derivative of cosine. So that's negative sine of x. So negative sine x over cosine x is what we're dealing with. And that's just a trig function. It can simplify to negative tangent x. So there's our derivative. And notice sometimes these simplifications are not just a good idea, it's almost survival. Without making that one critical step there, I'm not sure if I could really maneuver through this integral. I think I would just get stuck on the algebra. So now let's go to the 1 plus that same derivative squared. This will be 1 plus. The derivative squared is now just tangent squared. Negative sign falls off. I don't want to put 1 plus tangent squared inside there because I'm still trapped. I can't take that root across addition. I can't cancel that power 2 because of that addition sign. But anyone recall what that function could be written as? Good call. That's probably from memorizing that trigonometric substitution table, right? It just comes up all the time. So good call. That's nothing but secant squared x. Now we're in business. We have something to power 2, one single term. We can cancel the root there. So now the length is equal to, integrate from 0 to pi over 3, the square root of, and this is the major punchline. It's now just a secant squared x. This could potentially be a horrific problem, I should say, though. You have to be careful with these kinds of things because our textbook tends to give us stuff that's just sort of nice and works out. What would make this not nice is if you had a function that went this way, y equals secant squared x. I'm not sure what's, oh, here we go. Here's our function. Oh, not too sure what I was thinking on there. I was worried if it was negative, then we would have had a problem. But secant is always going to be a positive function. So we're okay on this one with the secant squared. Or hang on, getting my algebra mixed up. You need secant x. So the trouble with these square roots, just for a little discussion on algebra, is the square root of a for anything squared is the absolute value of a. And if your absolute value A shows up in a problem, it probably won't in this class. Our author doesn't ask those questions, but it could elsewhere, say an engineering class, for example. If the absolute value comes up, you have to find the region where it's positive, the region where it's negative, and split up your integral. It just turns into a big process. So if our problem looked like this, and we're going from 0 less or equals to x less or equals to pi over 3, then, well, we have just that little bit there, and thank goodness it's positive. That means when we go to cancel the root, we just get secant x. Again, that's pretty routine in our book because the author's not making big problems out of something that should have been smaller. But in other situations, that could be a real issue. So it's from 0 to pi over 3 of secant x. This one, as an antiderivative, comes up a good amount. It's a natural log of the absolute value. And the way I memorize it is if it's secant, secant comes up again. Then we have to go plus. And anyone remember the rest of it? Exactly. The way to think about it is when you differentiate this, secant times tangent comes up. But in the antiderivative, you get the natural log, secant plus tangent. Not the best mnemonic to memorize, but at least there's a sort of pattern there to think about. We'll evaluate this from 0 to pi over 3. And we do have to do the trig evaluation, so turning into a bit of a trig review here. So let's work out our trig functions first. Then we'll finalize this last evaluation pretty rapidly. We need to know secant pi over 3 to start. That's going to be 1 over cosine pi over 3. Cosine at pi over 3 is 1/2. So that's 1 over 1/2. And that means we're just going to get a 2 for secant pi over 3. Then do it again, tangent pi over 3. That's going to be sine divided by cosine. Sine at pi over 3 is root 3 over 2. Cosine at pi over 3 is 1/2. So just root 3 on that one. Let's do it again for 0. Secant 0 is not so bad because it's 1 over cosine 0, and cosine 0 is a 1. So is secant 0, just a dead-on 1. Tangent 0 is not so bad because you would put sine in the numerator at 0, which is 0, divide by cosine at 0, which is 1. So that one's a 0. And those are our 4 values that we have to use. So now that we've done that, it's a lot easier to write out this evaluation. It's going to be natural logarithm, absolute value. At pi over 3, we're going to be putting 2 for the secant plus root 3 for the tangent. Minus natural log absolute value. We just do it again. At angle 0, secant came out as a 1. Tangent came out as a 0. So then this simplifies even further. We have just positive quantities, so absolute value bars weren't necessary on the next steps. The whole length of this curve is natural log 2 plus the square root of 3. Natural logarithm of 1 is 0, so that should be our answer. Any questions, folks, with finalizing this one? Okay, and just to see if we're in the right neighborhood, oh, I don't have that function in there any longer. It was natural log cosine x. There it is. Let's zoom in on that just a touch. So the distance from here to here is square root of 2. And the actual length I have right here is natural log 2 plus square root 3. They are in the right neighborhood. So that would tell me excellent numerical evidence that really is on the right track for the exact length. So there's a lot more to say on these notes, but we've been working pretty hard. We got through an exam. I think this is a good stopping point for us today. When we come back, we're going to discuss fundamental theorem of calculus part 1 and how it relates to something called the arc length function. We're not doing a whole lot with it in these notes, but it ties into section 8.2, so it's like a segue. So we're going to finish this when we come back on Monday's class, and then start off section 8.2, surface areas next. Well, thanks for your hard work, folks. Getting through exam week is always tough. I know that you have other exams and other work to get through. But it starts to cool down once we're in week 6, week 7 in this class. So have a great weekend. If you have any questions, don't hesitate to reach out. Otherwise, I'll see you all in Monday's class. You betcha.
Mr. Jacobson, do you find if we just keep the absolute value on the natural log?
Yeah, that's totally fine. Absolutely. It's more of a stylistic choice at that point.
Yeah, cause I just prefer to keep the.
Cool. I mean, it's a good reminder that it should be absolute value in the anti-derivative anyways. So you're always just fine leaving it there, down there. Thanks, folks in Zoom. Actually didn't know you could break out a discussion in the chat there. Zoom is starting to get kind of involved these days. You too. Drive safe.